Welcome to a tutorial for a program to correct and adjust the performance of water-air heat pumps from rated values to conditions for your project in order to ensure comfort and account for auxiliary power. In order to do that, the things that need to be adjusted begin with the air entering the heat pump in the cooling mode at the rating conditions is 80.6 degrees F, which is outside the comfort zone and just a little warm for most people. In heating, the temperature is 68 degrees F, which is acceptable, but it can be adjusted. The power that's not considered that we have to correct for begins with the pump itself. The power to circulate water or the liquid through the external piping system needs to be added to the calculation. In addition, the power of the fan required to circulate air through the duct system and the grills and the filter needs to be included. This power also turns to heat, and so that heat must be deducted from the total cooling capacity of the machine. Fortunately, in heating, it's a benefit, so it's added to the capacity. The other thing that needs to be adjusted is the airflow. We need airflow that will guarantee a low enough velocity across this coil in order to remove moisture. And that's especially critical in humid and mixed climates. The other thing about the airflow is in the heating mode, if the airflow is too high, the heat pump will deliver uncomfortable air to the occupants, somewhat similar. You get the cold blow that you get with an air source heat pump. So we want to make sure that. The nice thing about the rating system, though, is it does cover a variety of entering water temperatures that can be adjusted easily. So let's go to the main program. And here we're going to show a little bit about the layout. The first thing is the yellow cells are cells for input, a variety of things. So, and then the output is, cells are in blue and green, and we don't want to type in them, okay? The other thing that we need to look at is this row up here is where the machines are rated at, okay? So the total cooling capacity in thousands of BTUs per hour, and the EER are rated in cooling at 59 degree F, 77 degree F, and 86 degree F for both the total capacity and the ER. In heating, the machines' heating capacity and the COP of the machines are rated at 32 degrees F, 50 degrees F, and 68 degrees F. Now you'll notice there's a couple of extra numbers in here for part load conditions. So the machines that have a variable speed capacity or a multi-speed capacity and operate in a part load mode, and the part load modes, they're rated at 68 degrees in cooling instead of 77, and in heating they're rated at 41 instead of 32. Okay. Now the next row is the things, units that we're looking at, and then here is a typical rating of a machine. This is a single speed 3-ton machine, and there are a variety of manufacturers that you can cut and paste or copy and paste the values, the rated values, into this row right here. Okay, so we'll do that quite a bit later on. This is the main column for input. This is the entering liquid temperature or water temperature into the machine in the cooling mode, and this is the corresponding in the heating mode. These two numbers are where you want your air temperature going into the machine to be in a comfort zone. So this is 75 in dry bulb temperature and 63 wet bulb, which represents about 50% relative humidity. In heating, the center comfort chart is at 70 degrees. So we're going to have the flow rate of the machine and water flow rate, GPM, and the airflow rate and CFM. You have a selection option here of different kinds of fans. We're going to be, in most cases, using the electronically commutated motors with the forward curve blade. Now the machine, the motors are quite efficient, but the blades, forward curve blades, are not really good equipment. So in this case, you can see the efficiency of the wire air efficiency is right around 30%, which is typical from research. External static pressure, this is the pressure loss through the ductwork and the rails and registers. And so typically this is a really good number for a 3-ton unit. Typically it ranges from, say, about 0.4, 0.3 up to as high as 1 inch. Okay, and so if you get that 1 inch, you're gonna be having a lot of power pulled by this fan. The filter loss represents a typical filter, a 1 inch filter, probably around a MERV 8 with a face velocity of 200 feet per minute. So it's partially loaded, it's not clean. All right, and then over here we have the pump power input, which we can use if we don't know what it is, and you know what the flow rate is for the machine, for the loop, the head loss around the external, just the piping. It doesn't include the head loss across the coil inside the heat pump itself. And you know the motor efficiency and the pump efficiency, you can get the wattage. And this is a 42%, which is fairly indicative of a small wet rotor circulator with an ECM motor. Okay, if you have a PSC motor, that number is probably going to be around 25 to 30. Now, so you can enter. The other thing that's input, we chose to use 7563 for the entering air temperatures. And so what we'll do is in this type, there 7563, well, these two numbers were put into here. And this is a bypass factor, which is typical for a coil, a 0.1. And then if you want a lower temperature or higher temperature, you have to type these numbers here down into here. These all represent about 50% relative humidity. Okay, so let's go ahead and get. The other thing we want to be careful about is we want these numbers here to be good. We want, since it's an ground source heat pump or a water air heat pump, we want this number to be up around 100. And we also want this number to be below 400, and this number to be somewhere between 2.5 and 3 GPM at full load. So you can see this is kind of high, so we're going to have to adjust this, get them down to where. The other thing that we're going to need to be looking at is this number right here. This is a sensible heat ratio. So that's what that's telling you, is that 81% of the cooling goes to reducing temperature and only 19% goes to removing moisture. So if we're in a mixed or humid climate, we want that number below 0.75. So we'll have to adjust the CFM to do that. So let's start doing that. We're going to change this CFM. Let's try to drop it down around 1,000 CFM. And then you can see that did the trick there. It got us down to 102, and CFM per ton is 372, which is pretty nice. And you see, drop that SHR down to 0.74. Now we got maybe we need to reduce the water flow a little bit. So let's try 8 GPM. And when we do that, what we have to do is take this number and type. You can't cut and paste. You can just type that number 32.1 into that cell, and you can see we're down around 3, which is a pretty good number. Okay, so We got 8 GPM, and so let's go ahead and put, when we size our pump, we'll put 8 there, okay? And this 25 foot of water, that would be the head loss through the exterior loop. It doesn't include the head loss across the coil itself, because that is considered in the rating. So you can see it up the KW to 0.09. So we'll put that in here at 0.9, and we'll see what we get. So we're looking pretty good. We got a machine that's a little less than 3 tons now, and we're good on the temperature, 101, and we're good on the SHR, okay? But what we need to do is just kind of get a feel for what happens. You can see this is the entering water temperature at 85, and it's rated at 86. So at 86, the standard says EER is 16, but you can see when we deduct the power and get the airflow down to where it should be and the pump power, it dropped it down to 13 and a half, okay? And it dropped the capacity, which was 35, down a little bit to 32, okay? So it does that when we add all these, the power for the pump and the fan, and make these other adjustments. Now, on the heating capacity, though, you can see the heating capacity that results is pretty much the same as the rating, okay? It didn't affect it much, because that basically, the fan heat helps keep that capacity up. Now, the COP, on the other hand, though, has dropped from 4.6 down to 3.7. So all in all, this is where you want to try to get your machine. These numbers here, typically you would be putting them in your schedule for your design documents, because usually the design documents don't really require you to put the pump power in. You put that in separately, okay? So I think we're doing pretty good here. So what we want to do now is we're going to look at a dual capacity machine. This manufacturer puts an S on their model numbers to indicate it's a single. So we're going to get the same, we're going to go get a 3-ton machine. It's got the T here, which is their symbol for dual capacity. Okay, so we'll go in here and we'll cut this. No, we'll copy it, I'm sorry. We'll copy it, and then we'll go in here and paste it right here into this mode right here. So you can see it's pretty much the same machine, but it didn't, we've left it alone. We kept the flow rates the same, so we can see it's all pretty well set up. You can see the capacity dropped a little bit from, and put this in there at 31.9, so it dropped just a tad capacity-wise, but the EER went down. I think it was like 13 and a half or 13.6. So these machines pretty much work the same way, except the dual capacity has valves and mechanisms to flip it into low or lower capacity, which causes a little bit of restrictions in the refrigerant flow and drops the efficiency just a tad, but not much, okay? So it looks pretty good, got a good temperature coming out of the machine and heating, GPM per ton around 3, and then we got a good SHR of 0.74. So let's go to the next step. The next step would be, let's see what it does at part load, okay? So here is the machine at part load that's got the T in it. So we're going to take that number right here and we're going to copy it, but we don't put it directly into there, because what happens is this machine is rated at 41 and 68 in cooling, and this correlation requires you to put it in at higher temperature. So this program, if we put it in there, I think it's already there, but let's go ahead and put it in there. Okay, so it corrects it to 32 and 77. So we go in here and we copy this. We're going to have to be careful now, because this row has some equations in it, okay? And so we don't want those equations in here. We just want the numbers. So we go back up here and we click on this and we paste values, not the equation. We paste the values, okay? So you can see the capacities in cooling and heating drop down, okay? So we'll recognize that. We'll drop this down to and the cooling mode, okay? And it moved around a little bit. So anyway, you can see that our CFM was high, so our temperature blowing on people in the rooms 94, and then the sensible heat ratio is not any good. It's 85. We're not getting much dehumidification. So what we're going to do, let's try dropping this down to, let's just go to 750, okay? See what happens. Yeah, that did good. It got us down to 382 CFM per ton and 100.5 going on, coming out of the machine, and our sensible heat ratio is 75. So that did the trick. I'm going to have to change this up a little bit to match. Okay, so we're a little high on the airflow, but you know, everything's looking good in terms of this sensible heat ratio and the temperature coming out. Now, what we're going to do on this one, though, is we're going to assume that because of dual capacity, and we're not using a variable speed pump, okay? So basically, the power, the flow rate, and the power are going to stay the same. But if you had a variable speed pump, we'll show you what to do that a little bit later, okay? But this still, everything looks pretty good. But what we've done is, of course, what the dual capacity machines are done for, because it raised the VER and cooling up to 15, and you remember the single speed machine was 13 and a half, okay? So basically, we've improved the efficiency at part load, so that's what we wanted to do, okay? But again, let's see, yeah, well, everything looks pretty good, so that's the dual capacity machine doing what it's supposed to do, okay? Now, let's go one step further and see what happens when we do the same thing for a variable speed machine. So down here is a manufacturer of that also makes variable speed, but this is their single speed, compact. It's a really efficient machine. So we'll go ahead and copy it, okay? And this is at full load, so we'll come back up here and we'll paste it in here, okay? So we're going to have to go back to the higher flow rates. We're going to change this. That's 28.9. So it's not a real strong 3-ton machine. Got us a good thing, but see here, we want to kick this CFM up to 1,000. Okay. See, we went a little past that, so let's go to say 950. See what happens there. 383. We got a good SHR. Let's go down a little bit more to try to get that temperature up closer to 100. So let's go to 900. Okay. So we got it right at 100. Okay. So right, yeah. So we're right at 100, and the GPM, we could drop that down a little bit. Let's knock it down to 7. Okay, and that drops the change this, and it drops the fan power down just a little bit. So we'll change that to 0.08. Okay, so now let's see what we got. We got a little bit below 100, but it's still pretty good. This is almost the same, so we're not going to change that too much. So we're looking at something, got a 7.4 on the sensible heat ratio, and we got almost 100 degree air. So we're in good shape, but you can see this machine actually has a really good EER. You can see at full load it's 15.5 when we put all this. And the COP is 3.8, so it's gone down a little bit compared to what it okay. So we're in good shape here. But remember that number, 15.5 and 3.8, okay? And that's a single-speed machine, high-efficiency single-speed machine. Now, let's go to the same manufacturer's variable-speed machine, okay? So we're going to pick the same the capacity, 3-ton, nominal 3-ton. You can see they've got a lot of water flow, 13 GPM for a 3-ton machine, so we'll have to fix that. So we're going to copy that, okay? And then we'll go back up here and we'll stick that thing in here. We'll paste it, whoops, just paste that in there, okay? So you can see this is pretty much the same, okay? Let's see, what do we got here? One thing about these machines is they deliver, the variable speed machines deliver a lot hotter air than typical. But the bad news is, look at the ER, okay? This is a machine that you paid a lot more money for, but at full load, it's got, about 20% lower EER than the single-speed machine. Now, this is a result of the fact that these machines operate at much higher speeds than your single speed. And what that does is it reduces the thermodynamic efficiency of the compressor, which when you reduce it will not only reduce the EER, but it will also provide more heat. That's why this is up around 110. So let's mess with this a little bit to see if we need to do anything. Let's see. No, it looks pretty good. See, we got 365. Oh, we got a real good SHR. Let me kick this up just a little bit, maybe to kind of match what was done before. So 382, 208, nice, 0.75. But see, the ER didn't change much. So ER is 12.4. This is still at 0.08, okay? So you can see this is what happens when you have a variable speed machine running at full load, okay? Now, what we're going to do now is one more step. We're going to go down and see what the machine will do the part load. Now, the variable speed machine will reduce a whole lot more than a dual capacity. So you can see this machine goes down, as a 3-ton machine, goes down to 1 ton, okay? But one of the things you want to notice is the ER is pretty high, 20.4 at 86. But they're blowing 650 CFM across 1 ton and 7 GPM across 1 ton. So that needs to be fixed. So let's go ahead and do this. We'll go ahead and copy this, all right? And then we'll go back and do that thing where we adjust the performance at equal temperatures. So we'll paste it. Oops, let's see. Let me make sure I copied that. So this is the part load value. We're going to copy it, all right? And then we're going to paste it into this corrector here. Paste, okay? And you can see there's the numbers. But I'm going to change the nameplate on it to what it is, and I'm going to put in there that it's a corrected value. It's not the true value. Okay? So we're ready to cut. I'm sorry, cut. We're ready to copy. And again, we have to go up there. Remember, we're going to have to, see, did I copy that? I guess I copied it. Let's see. Copy, and we go up here, and we will paste values, okay? So you can see we're way over on the CFM. We need to cut that down to something. See, we're going to go 10.7. It's going to go down a little bit below that. So we're still way over there. So let's drop this down to values for a machine that's a little bit less than all right, so it's dropped it down to 2.5 GPM per ton and 350 CFM. So we're going to adjust this back to 9.9, and let's see what happens here. This is still a little high. You see we have a high sensible heat ratio. Now, this is bad, especially at part load, because your part load, you got to have more dehumidification ratio. So what we're going to have to do is let's try to go down to 300 CFM to get that down. 70. We've got nice hot air, and we got 0.74. So we're pretty well equal. But what we'll do this time, you paid this extra money for a variable speed machine, why don't you just go ahead and get you a variable speed pump, so when the thing goes into part load, you can drop it down. So let's change this 2.5 GPM, and of course, when you lower the flow rate, you're also going to lower the head loss. So let's put this down around probably 8 foot ahead. Okay, efficiency is still about the same. The machine is pretty flat. Okay, so we got, what do we got here? We got 370, 107, nice and hot air, 3 GPM per ton. And you can see our looking pretty good. A little high on the GPM, that's okay. And our pump, we're going to change that from 0.08 to 0.1. Okay, so now here we are. You can see our part load for this particular machine is increased quite a bit from the 12, but you also note that this is not much different than that variable speed, the single speed machine. It was just pretty much the same value. So, and a lot of you are going to say, well, you're not being fair to variable speed. You don't like them because they're so complicated, and I'm saying, well, I think you need to look real hard at how we do these calculations. So I put a sheet here that shows you how to adjust. This is all straight out of HVAC calculations, and pretty straightforward. You just have to have the right information to show you how to correct from the rated value of a single speed machine to the actual value. And then here is a correction for variable speed PowerPoint. You can see, this is from the directory, tells you have a 41 EER and a 7.5 or 7.6 COP. But when you do all this correcting like you should, then you can see what is really quite a bit different. So I hope this helps you provide knowledge so that you can provide your clients with comfortable and highly efficient equipment.